Hello students, welcome to the channel Physics Regulars. If you are watching this video, please subscribe to the channel. In this video, you are going to learn class 12th physics chapter Nuclei. Okay, when we observe our surroundings, we observe so many objects or matters. If you take any of the object and break it into smaller and smaller pieces, you will get very small particle. This small particle is called as atom. What this atom consists of? Is there any empty space inside the atom? Or something is there? Scientists made experiment on this and they come to know there is something inside the atom called nucleus. And electrons are revolving around the nucleus. About this nucleus you are going to study in this chapter. Here nuclei is the plural form of nucleus. Okay, we will see the overview of the topic. Here you will study constituents of the nucleus. That means what nucleus contains, composition of nucleus, and also nuclear mass, nuclear size, nuclear stability, and also nuclear phenomena like radioactivity, nuclear fission and nuclear fusion. These are the concepts you will study in this chapter. Okay, let us start. Here, since nucleus is very small, it is difficult to measure nuclear mass in terms of kg. So, scientists decided to give separate unit to measure nuclear mass. This unit is called as atomic mass unit and the symbol is small u. Here, atomic mass unit is defined as 1/12 the mass of one carbon-12 atom. What it means? One atomic mass equal to 1 atomic mass unit is equal to mass of one carbon-12 atom divided by 12. Here, why carbon-12 atom is taken? Why carbon-12 atom is taken as standard? Because carbon-12 atom is easily available in nature. It is abundant in nature. And this value divided by 12. Why mass of carbon-12 is divided by 12? Because nucleus of carbon-12 contains 6 protons and 6 neutrons. So when you divide mass of carbon-12 by 12, you will get individual mass of proton or neutron. It will be more clear when we complete composition of nucleus. When we complete 5th slide, it will be more clear. Okay? Here mass of one carbon-12 atom, they name it. That is 1.9926 into 10 raised to minus 26 kg. Where this divided by 12. You will get 1.6605 into 10 raised to minus 27 kg. This is the value of one atomic mass unit. Therefore, 1 atomic mass unit equal to 1.6605 into 10 raised to minus 27 kg. Here, small u is the symbol. Here, our intention is to measure nuclear mass. But they have given the name atomic mass unit. Why? Because 99.9% of the mass of the atom is contributed by its nucleus. So mass of the atom is almost equal to mass of its nucleus. Hence, we use the same unit to measure nuclear mass as well as atomic mass. Can we measure this nuclear mass using normal weighing machine available at the grocery shop? Is it possible? No. There is a special device to measure mass of nucleus called mass spectrometer. Okay, I hope this atomic mass unit is clear to you. Now moving on to composition of nucleus. Scientists, they were studying different atoms, masses of different atoms, and they surprised because they got different types of atoms. Different types of atoms means atoms with different masses. Atoms of same element having different masses, and they named it as isotope. Here iso means same, tope means place. Isotopes are atomic species of the same element having different masses. Why the name isotope? Isotope is a Greek word. This means same place. Here these elements remains in the same place in the periodic table. Even though their mass is changed, they remain in the same place in periodic table because their chemical properties remains as it is. Because chemical properties are remaining depending on outer electrons. So they remain in the same place, hence the name isotope. Isotopes are nothing but atomic species of same element having different masses. Here atomic species means identified atom. Suppose X is atom, this atom is identified with its atomic number and mass number. This identified atom is nothing but atomic species. Okay? Let me clarify this with examples. You know the element hydrogen. For hydrogen, there are 3 isotopes. For hydrogen, there are 3 isotopes. 1H1 called protium, another one 1H2 called deuterium, and third one is tritium 1H3. Here protium, deuterium and tritium are the isotopes of hydrogen having different masses. Here this protium is 99.9% of protium is having 99.9% of relative abundance. Relative abundance means its availability compared to other isotopes, and these two are rarely available. This tritium is produced artificially in the laboratories. Because of its special properties, it is needed in research and technology. So tritium are produced in laboratories artificially. Okay, these are about isotopes of hydrogen. Let me take one more example, chlorine. For chlorine, there are 2 isotopes, chlorine 35 and chlorine 37. These are the isotopes of chlorine. Here in nature, every element occurs in the form of mixture of isotopes. Those mixture of isotopes are taken and their average mass is calculated. Let us see how average mass of the atom, how average mass is calculated. Okay. We will take the example of chlorine only. For chlorine, there are 2 isotopes, chlorine 35 and another one, chlorine 37. Chlorine 35 and chlorine 37 are the isotopes of chlorine. Here, these 2 isotopes are taken and their average mass is calculated. That is the average atomic mass of chlorine. Based on their relative abundance, average atomic mass is calculated. Okay, we will see that. Here, for chlorine 35, accurate mass of chlorine 35 is here 34.98 atomic mass unit, and its relative abundance is 75%. That means its availability is 75% compared to chlorine 37. Okay, Chlorine 37 is having mass 36.98 atomic mass unit and its relative abundance is 25%. Now based on their relative abundance, average atomic mass is calculated. Here average atomic mass equal to, I use the short form for average. Average atomic mass equal to relative abundance into its mass. For chlorine 35, mass is 34.98 atomic mass unit, plus for chlorine 37, abundance is 25%, its mass is 36.98 atomic mass unit. If you calculate, you will get nearly equal to 35.5 atomic mass unit. This is the average atomic mass of chlorine. This is how average atomic mass is calculated. Okay. Okay, coming to next slide. Here hydrogen has three different isotopes. They are protium, deuterium and tritium. These are isotopes of hydrogen. And this protium is 99.9% available. So protium is taken. Here protium, nucleus of protium means single proton. Protium is the lightest isotope among all the isotopes and it contains single proton, only one proton in its nucleus and one outer electron, one electron revolving around single proton. Here mass of protium minus mass of outer electron is the mass of proton. Mass of protium minus mass of outer electron is the mass of proton, and this mass of proton is equal to 1.67 into 10 raised to minus 27 kg. Here mass of proton is equal to 1.672 into 10 raised to minus 27 kg. Here this proton carries 1 unit of fundamental charge, that means 1.6 into 10 raised to minus 19 coulomb. Proton carries 1 unit of fundamental charge, positive charge, and outer electron carries 1 unit of fundamental charge but negative charge. Proton positive charge, outer electron negative charge. Because of positive and negative charges, atom is neutralized. Suppose there are z number of protons in a nucleus of an atom, there will be z number of outer electrons. Hence charge is neutralized. Atom is neutralized. This is about proton inside the nucleus of an atom. Here charge of the proton is plus E. Suppose there are z number of protons, charge on the nucleus will be plus Ze. Free proton is stable. That means sometimes this proton will come out of the nucleus. This free proton is stable. Okay. Now it is clear what is there inside the nucleus? Proton. Okay. Let us go for next slide. Now observe the masses of isotopes of hydrogen. Hydrogen isotopes means protium, deuterium and tritium. Observe the masses of isotopes of hydrogen. They are in the ratio 1:2:3. Now we can say deuterium and tritium are masses of deuterium and tritium are in the ratio 1:2:3. They are the integral multiples of protium. Masses of protium, deuterium and tritium are in the ratio 1:2:3. It shows that in addition to proton, because hydrogen nucleus contains single proton, But here there are extra masses in nucleus of protium and deuterium. It shows that some extra mass is there inside the nucleus in addition to proton. Since atom is neutralized, this extra mass is from some neutral particle. What is that neutral particle? This neutral particle is called as neutron. Let us see what is neutron. In 1932, James Chadwick discovered neutrons. He was doing an experiment. He took beryllium atom and the beryllium atom is bombarded with alpha particles. Alpha particles means helium nucleus. When beryllium atom is bombarded with alpha particles, he observed some neutral radiations. At that time, at the time of 1932, scientists believed that there is only one neutral radiation, that is electromagnetic radiation. But this neutral radiation observed by James Chadwick was carrying different energy than electromagnetic radiation. It behaved as if it is heavy mass. From conservation of energy and momentum, James Chadwick successfully calculated mass of this heavy particle called neutrons. That mass of neutron is equal to 1.674 into 10 raised to minus 27 kg. This is the mass of neutron. Here, mass of neutron is nearly equal to mass of proton. Mass of proton is equal to 1.672 into 10 raised to minus 27 kg. Mass of neutron is 1.674 into 10 raised to minus 27 kg. They are nearly equal, but mass of nucleus is slightly greater than mass of neutron is slightly greater than mass of proton. Free neutron is unstable. Sometimes neutrons will be outside the nucleus. They are free electrons. When they will be free, that you will study later. In the next topic, you will study about that. Sometimes these free neutrons will be free, and these free neutrons are unstable. That means they can stay for 1000 seconds, nearly equal to 1000 seconds. Then neutron will be converted into proton by emitting electron and antineutrino. It can stay for 1000 seconds. Then it decays into proton by emitting proton, electron and antineutrino. Here antineutrino is another elementary particle which is having very less mass and zero electric charge. Okay, this is about neutron, and also mean life of free neutron is 1000 seconds. That means when neutron is free, it can stay for 1000 seconds. After that, it will decay. In nuclear physics, we use some notations. Z represents number of protons inside the nucleus. N represents number of neutrons inside the nucleus. And A represents number of nucleons, total number of protons and neutrons. You can remember like this: A for adding both protons and neutrons, A for adding. Here we also use one term, nucleon. Nucleon means either proton or neutron. And one more term is nuclide. Nuclide means identified nucleus. Suppose X is nucleus. This nucleus is identified with its number of protons and total number of nucleons. This is identified nucleus. We also call it as nuclide. Now it is clear what nucleus contains. Nucleus of the atom contains number of protons and number of neutrons. If I explain one atomic mass unit now, it will be more clear to you. What is one atomic mass unit? Mass of one carbon-12 atom divided by 12. Why it should be divided by 12? because carbon 12, nucleus of carbon 12 atom contains 6 protons and 6 neutrons. When you divide mass of one carbon 12 atom by 12, it will give you value of mass of single nucleon inside the nucleus. So we should divide mass of one carbon 12 atom by 12. Okay, this is about composition of nucleus. Now we will see what are the types of atoms we observe depending on their number of protons and neutrons. Atoms are classified into different categories. We will see that. Here, isotopes, isobars and isotones. Isotopes means atomic species of same element having different masses. Isotopes are of same element having different masses. There will be same number of protons inside the isotopes. You can remember like this. P means protons same. Example, isotopes of hydrogen 1H1, 1H2 and 1H3. Protium, deuterium and tritium. Next, isobars. Isobars are atomic species of different element having same number of mass, same mass number. Here bar means mass or weight. You can remember like this, A for mass number. Isobars are atomic species of different element having mass number same. For example, carbon 14 and nitrogen 14. Their atomic numbers are 6 and 7 respectively. Their mass number is same here. So they are isobars. Next one is isotones. Isotones are atomic species of different element having same number of neutrons. For example, I will take the example of carbon and nitrogen only. Carbon 14 and nitrogen 15. Their atomic numbers are 6 and 7 respectively. A minus Z is same for both carbon and nitrogen. A minus Z means number of neutrons. You can remember like this, N for neutron. In isotones, there will be same number of neutrons. Neutrons same. In isotopes, protons same. In isobars, bar means weight. Here you can remember like this, A for mass. Isobars are having same mass number. Isotones are having same neutron number. Okay, these are the different types of atoms we observe. Okay, moving on to next topic, that is size of nucleus. Scientists Rutherford and his teammates, they were decided to study about size of nucleus, and they did one experiment. Rutherford did one experiment called alpha scattering experiment. You will study about this alpha scattering experiment in detail in atom chapter. What they did in this alpha scattering experiment? Rutherford took very thin gold foil and alpha particles are projected on very thin gold foil. Alpha particle means helium nucleus. You can visualize this experiment using one example. Imagine you are in a dark room, in invisible place, and you have a ball. By hitting a ball against the wall, ball bounces back. By doing like this, you can determine the distance of the wall. If ball takes much time to come back, that means wall is far away. If ball takes less time to come back, that means wall is near. If ball bounces back, making some angle by deviating, means it may be wall edge or there may be edge. If ball passes straight and it never comes back, means there is no wall. In the same way, you can visualize alpha scattering experiment. When alpha particles, when helium nuclei are projected on thin gold foil, most of the alpha particles deflected back, and some of the alpha particles, they deviated making some angle, and some of the alpha particles passed straight, revealing that there is empty space inside the atom. Most of the alpha particles deflected back. It shows that there is dense positive core inside the nucleus. By hitting the nucleus, alpha particles are deflecting back. Alpha particles are positively charged and nucleus is positively charged. Because of strong electrostatic repulsive force, alpha particles are deflecting back. By doing this experiment, Rutherford estimated the radius of nucleus. That is, radius of nucleus is directly proportional to cube root of its mass. Instead of alpha particles, they also used fast moving electrons to get more accuracy, and they determined the radius of nucleus. Radius of nucleus is given by r equal to r naught into a raised to 1 by 3, where r is radius of the nucleus, r naught is constant, which is equal to 1.2 Fermi. 1.2 Fermi. Fermi means 10 raised to minus 15 meter. And A is mass of the nucleus. Here, size of the atom is in terms of Fermi, 10 raised to minus 15 meter. And size of the atom is in terms of angstrom. Angstrom means 10 raised to minus 10 meter. See here, size of the atom is million times bigger than size of the nucleus. Okay, this is about radius of the nucleus. Next, we will see what is the volume of the nucleus. Here, nucleus is assumed to be spherical in shape. Volume, what is volume of the sphere? 4 by 3 pi r cube. Volume of the sphere is equal to 4 by 3 pi r cube. Using this, you can find volume of the nucleus. Here, r equal to r naught into a raised to 1 by 3. Substitute the value of r. Therefore, volume of the nucleus is equal to equal to 4 by 3 pi, substitute the value of r here, r naught into a raised to 1 by 3 whole cube. You will get volume of the nucleus is equal to 4 by 3 pi r naught cube a raised to 1 by 3 cube a. That is, volume of the nucleus is given by 4 by 3 pi r naught cube a. This is the volume of nucleus. It shows volume of the nucleus is directly proportional to its mass. V is directly proportional to A. This is about volume of the nucleus. Then what is density of the nucleus? What is density? Mass by volume. Okay, we will say the density of nucleus. Density rho is given by mass by volume. What is mass of the nucleus? Sum of masses of individual nucleon, that is Z into number of protons into mass of single proton plus number of neutrons, that is A minus Z into mass of neutron, divided by volume of the nucleus, that is 4 by 3 pi r naught cube A. 4 by 3 pi r naught cube A. Therefore, density of the nucleus equal to, here consider mass of proton is nearly equal to mass of neutron. So consider mass of proton equal to mass of neutron. Mass of proton is nearly equal to mass of neutron. Therefore, density of nucleus equal to Z into mass of neutron plus A into mass of neutron minus Z into mass of neutron divided by 4 by 3 pi R naught cube A. Here Z into mass of neutron, Z into mass of neutron cancels out. Remaining is A into mass of neutron divided by 4 by 3 pi R naught cube A. A cancels out. What is density of nucleus? Equal to mass of neutron divided by 4 by 3 pi R naught cube. This is the density of nucleus. You know the value of mass of neutron, you know the value of R naught. Substitute the values. By substituting, you will get density of nucleus is nearly equal to 2.3 into 10 raised to 17 10 raised to 17 kg per meter cube. This is the density of nucleus, this one. Here density of the nucleus is equal to almost equal to 2.3 into 10 raised to 17 kg per meter cube. Here it shows density is constant for all the nuclei. Density is independent of its mass. Density is independent of A. So density is constant for all the nuclei. Here density, observe the density of nucleus, it is in terms of 10 raised to 17 kg per meter cube. Density of the gold is about 19,000 kg per meter cube. Density of the nucleus is in terms of 10 raised to 17 kg per meter cube. See how dense is the nucleus. This is about nuclear density. This is the previous year NEET question. The question is the ratio of nuclear densities and nuclear volumes of iron and helium are respectively. You know that density is constant for all the nuclei and volume is proportional to its mass. V is directly proportional to A. Let us solve it. Density is constant for all the nuclei. Hence, density of iron rho, density rho of iron by density of helium. They are constant, therefore ratio is 1:1. Ratio equal to 1:1. Next one is ratio of volumes. We know that volume of the nucleus is directly proportional to its mass number. Therefore, volume of iron by volume of helium becomes ratio of volume of iron to volume of helium becomes ratio of their masses. Mass of iron by mass of helium. Therefore, ratio equal to, what is mass of iron? 56. Mass number 56. And ratio of mass of helium is 4. 56 by 4, that is 14 by 1. Therefore, ratio is ratio of volumes of iron to the helium is in the ratio, they are in the ratio 14:1. Correct? Okay, hence option 3 is the right answer. One is density ratio 1:1 and mass volume ratio 14:1. Okay. This is about size of the nucleus. It completes composition of nucleus, mass of nucleus and also size of nucleus. Now moving on to next topic, that is nuclear binding energy. This is the summary: radius of the nucleus, volume of the nucleus and density of the nucleus. Okay. Before going to nuclear binding energy, it is important to know one well-known equation given by the scientist Albert Einstein. This equation relates mass and energy. This equation says mass is also one form of energy. What is this equation? Do you know this? You might have heard, that is E is equal to m into c square, where E is energy of the particle or object or body, m is rest mass of the body and c is velocity of light, that is 3 into 10 raised to 8 meter per second. This equation is very important. E is equal to m into c square. This equation is very important because using this equation we will understand binding energy of the nucleus, stability of nucleus and also nuclear reactions like nuclear fission and nuclear fusion. Here, small amount of mass can also give large amount of energy. We will see one example. Calculate energy equivalent of 1 gram of substance. Here mass is 1 gram. Let us see how much of energy is given by 1 gram of substance. Here given mass equal to 1 gram, which is equal to 10 raised to minus 3 kg. We know that energy is equal to mass into c square, where m is mass, c is velocity of light. What is mass here? 10 raised to minus 3 kg. Velocity of light is 3 into 10 raised to 8 meter per second. When you calculate, you will get 10 raised to minus 3 into 9 into 10 raised to 16. That will give you 9 into 10 raised to 13 joule of energy. See here, 1 gram of substance can give 9 into 10 raised to 13 joule of energy. Here, small amount of mass will give large amount of energy. Okay. Next we will see nuclear binding energy. Here, what is mass of nucleus? Mass of nucleus is nothing but mass of nucleus equal to sum of masses of its individual nucleons, correct? Number of protons inside the nucleus into its individual mass of proton, plus number of neutrons, that is A minus Z, into mass of neutron. This must be the mass of nucleus. But when mass of nucleus is measured, actual mass of nucleus is lesser than sum of masses of individual nucleons. Here, small amount of mass is missing. Small amount of mass is lost. This lost mass is nothing but mass defect. Mass defect is equal to sum of masses of individual nucleons minus measured mass of nucleus. Where this mass gone? This mass is converted into energy. For example, consider oxygen. Nucleus of oxygen contains 8 protons and 8 neutrons. Here, mass of the oxygen nucleus must be number of protons into individual mass of individual proton plus number of neutrons into mass of individual neutron. That is equal to Z. Here in oxygen nucleus number of protons are 8 into mass of individual proton, that is 1.0072 atomic mass unit, plus A minus Z, number of neutrons are also 8 into mass of neutron is 1.00866 atomic mass unit. When you calculate, you will get mass of nucleus as expected mass is 16.127 atomic mass unit. So, when you calculate, you will get 16.127 atomic mass unit. But when mass of nucleus of oxygen is measured using mass spectroscopy experiment, the actual mass, measured mass is 15.99 atomic mass unit. Observe here, there is a difference between expected mass and measured mass. Here some mass is lost. In oxygen nucleus, that mass defect is 0.1369 atomic mass unit. Some mass is lost. Here in oxygen nucleus, lost mass is equal to 0.936 atomic mass unit. That lost mass is nothing but mass defect. And energy associated with this mass defect is called as binding energy. Next, we will see binding energy. What is binding energy? When we break the nucleus, we have to apply to break the nucleus into its individual nucleons. So, energy required to break the nucleus into its individual nucleons is called binding energy. Or, when nucleons combine to form nucleus, they will release energy. That released energy is nothing but binding energy. There are two cases. When nucleus break into its individual nucleons, to break the nucleus into its individual nucleons, we have to apply energy. That required energy is binding energy. Or when nucleons combine to form nucleus, they will release energy. That released energy is binding energy. Here energy is required. Required energy is binding energy. Here released energy is binding energy. Here when nucleus is break into its individual nucleons, we have to apply energy, that is binding energy. This explains the process of nuclear fission. When nucleons combine to form nucleus, they release energy. This binding energy explains the process of nuclear fusion. And binding energy is given by EB equal to delta M into C square, where delta M is mass defect and C is velocity of light. Here our intention is to study nuclear stability. To study nuclear stability, we have to understand binding energy. Here binding energy is equal to delta M into C square. But to understand nuclear stability, this binding energy, total binding energy of the nucleus is not sufficient. Then which will explain nuclear stability? That is, when you divide total binding energy by its mass, it will give you binding energy per nucleon. Binding energy per nucleon is equal to binding energy by its mass. This binding energy per nucleon is very important because it is the representative of stability of nucleus. Binding energy per nucleon is more means nucleus is more stable. Using binding energy per nucleon, we understand nuclear stability, and also it explains why some nuclear reactions takes place. Binding energy per nucleon. More binding energy per nucleon means the nucleus is more stable. This is about binding energy per nucleon. This is one example in which we have to find energy given by one atomic mass unit. First in joules, then in mega electron volt. Using this, express the mass defect of oxygen 16. Let us solve it. What is given here? That is mass equal to 1 atomic mass unit. Here, instead of small u, we also use AMU. Both are correct. 1 atomic mass unit equal to 1.6605 into 10 raised to minus 27 kg. What we have to find? Energy in terms of joule first. We know that energy is equal to m into c square. What is m? M is equal to 1.6605 into 10 raised to minus 27 kg. Velocity of light is 2.997 into 10 raised to 8 whole square. Do the calculations, you will get around 1.49 into 10 raised to minus 10 joule. Hence, energy given by one atomic mass unit is equal to 1.49 into 10 raised to minus 10 joule. We have solved one example in that we have calculated how much energy is given by 1 gram of substance. Here we are calculating energy given by one atomic mass unit. But first we have to find energy in terms of joule, then we have to find energy in terms of mega electron volt. Here electron volt is different unit to measure energy. In subatomic level, we use electron volt as unit for energy. Here 1 electron volt equal to 1.602 into 10 raised to minus 19 joule, or 1 joule can be written as 1 joule equal to 1 by 1.602 into 10 raised to minus 19 electron volt. Reverse. Okay, now we have to find energy in terms of electron volt. Therefore, energy equal to, energy in terms of joule is 1.49 into 10 raised to minus 10. Divide it by 1.602 into 10 raised to minus 19. How much you will get? You will get around 0.9315 into 10 raised to 9 electron volt. Now you have energy in terms of electron volt, but you have to find energy in terms of mega electron volt. Therefore, energy equal to, mega means 10 raised to 6. energy equal to 931.5 mega electron volt. This is the energy given by 1 atomic mass unit, that is 931.5 mega electron volt. Now express the mass defect of oxygen 16. This is oxygen 16 in terms of mega electron volt per c square. Here why the unit of mass is mega electron volt per c square? I will write it here. E is equal to m into c square, correct? Therefore, m equal to E by c square. What is the unit of energy? Mega electron volt by c square. Hence, mega electron volt per c square is the unit for mass. Therefore, delta m, mass defect of oxygen in terms of mega electron volt per c square is, multiply this value with 931.5. That is, what is the given value? 0.1369 atomic mass unit. Multiply this with 931.5. Now you will get energy in terms, you will get mass defect in terms of mega electron volt per c square. Calculate it, you will get the value in terms of mega electron volt per c square. This is how energy in terms of joule can be converted into mega electron volt. Here is a graph which shows how binding energy per nucleon varies with mass number. X-axis represents mass number and y-axis represents binding energy per nucleon in terms of mega electron volt. And these are the observations from the graph. Observe the graph carefully. For mass number less than 20, for lighter nuclei, the graph is sharply increasing. The graph is increasing steeply. That shows for lighter nuclei, for mass number less than 20, for small increase in mass number, there is large change or increase in binding energy per nucleon. In this region, for mass number less than 20, lighter nuclei, for small increase in mass number, there is large increase in binding energy per nucleon. Here lighter nuclei, they try to get more binding energy per nucleon. More binding energy per nucleon means they try to become more stable. Hence, lighter nuclei combine to form heavier nuclei to become more stable, to get more binding energy per nucleon, and they release energy. That means lighter nuclei, to become more stable, they undergo fusion. After that, for mass number 30 to 170, in this region, the graph is almost flat. That shows nuclei under this region are having constant binding energy per nucleon, almost constant binding energy per nucleon. That means they are stable. And iron 56 is having maximum peak. This is the stable, most stable nuclei. Iron 56 is the most stable nuclei, which is having binding energy per nucleon about 8.7 mega electron volt. After iron 56, graph is slowly decreasing. For heavier nuclei, for mass number greater than 170, graph is gradually decreasing, which shows binding energy per nucleon decreasing for heavier nuclei. These heavier nuclei like uranium-238, these are also very unstable. Unstable nuclei try to get more binding energy per nucleon to become more stable. Hence, heavier nuclei split and release energy. To become more stable, heavier nuclei split into fragments and release energy. That means heavier nuclei, to become stable, they undergo fission. Let us see the summary observations from the graph. What I told is written here. First point is binding energy per nucleon increases very fast from hydrogen to mass number around 20. For mass number less than 20, their graph is increasing suddenly. Next is for lighter nuclei, for mass number less than 30, as mass number increases, stability also increases. Lighter nuclei, they try to become more stable. For as their mass increases, stability also increases. Hence, they try to get more mass number. That means they try to combine and they get more binding energy per nucleon. Combined heavier nuclei, formed heavier nuclei will have more binding energy per nucleon. Hence, lighter nuclei try to become heavier nuclei by combining and release energy. And third point is the curve becomes almost flat between mass number 30 to 170. In this region, the curve is almost flat, which shows binding energy per nucleon is constant for nuclei under this region. Next point is for iron 56, binding energy per nucleon is maximum about 8.75 megaelectron volt. Iron 56, nuclei of iron 56 is the most stable nuclei. After iron, as mass number increases, binding energy per nucleon also slowly decreases. Here you can observe, after iron 56, the curve is slowly decreasing. As mass number increases, binding energy per nucleon is decreasing. For heavy nuclei, A greater than 170, like uranium 238, have lower binding energy per nucleon, therefore they are less stable. Heavier nuclei are less stable. And fusion of lighter nuclei releases energy because binding energy per nucleon increases. If binding energy per nucleon increases, there will be energy released. Here lighter nuclei becomes heavier nuclei by combining and release energy, because when they combine to form heavier nuclei, their binding energy per nucleon increases. Binding energy per nucleon increases means there will be energy released. Okay, next point is fission of heavy nuclei releases energy because binding energy per nucleon increases for the resulting fragments. Heavier nuclei are unstable. They try to get more binding energy per nucleon. They split. Hence, they split into fission fragments. And these fission fragments are having more binding energy per nucleon. Fission products have more binding energy per nucleon. That means there is energy released. Heavier nuclei, to become more stable, they split into fragments and release energy. These are the observations from the graph. Hence, this graph helps us to study how binding energy varies with mass number, and also we can compare stability of different nuclei. We know that nucleus contains number of protons and number of neutrons. Because of number of protons inside the nucleus, there must be electrostatic repulsive force inside the nucleus, correct? But how these nucleons are tightly bound inside the nucleus? What is the reason? The reason is strong nuclear force. Here I use the term nuclear force frequently, which means strong nuclear force. One more force is there, that is weak nuclear force, but here you are studying only strong nuclear force. What is this strong nuclear force? Strong nuclear force is a fundamental force which acts between nucleons inside the nucleus. Then what are the natures of this strong nuclear force? We will see that. Nuclear force is very strong force. Strong nuclear force is the strongest force in nature. It is stronger than electrostatic Coulomb force and gravitational force. Even gravitational force is weaker than electrostatic Coulomb force. And this strong nuclear force is stronger than electrostatic Coulomb force. Hence, strong nuclear force is the strongest force in nature. And next point is short range force. Nuclear force is a short range force. It acts between 1 to 2 Fermi. Fermi means 10 raised to minus 15 meter. For very short distance, for less than 0.5 Fermi, its nature is repulsive. And for greater distance, greater than 2 Fermi, its effect is 0. For larger distance, there is no effect, the effect of strong nuclear force is 0. For very short distance, for less than 0.5 Fermi, it is repulsive. Its nature will be repulsive. Near 1 Fermi, nature of strong nuclear force is attractive. And it acts between all nucleons. This strong nuclear force is charge independent. Hence, it acts equally between proton and proton, proton and neutron, and also neutron and neutron. This force is charge independent. And also, this shows, the strong nuclear force shows saturation. That means, strong nuclear force will be, it will act for nearby nucleons. Suppose you consider 2 nucleons, imagine 2 nucleons, there are number of nucleons in between them. The effect of you considered nucleon for nucleon at larger distance will be 0. Effect of strong nuclear force for nucleon at larger distance will be 0. It will act for nearby nucleons only. For larger distance, effect is 0. Hence, nuclear force shows saturation. Force will be saturated for larger distance. It will not affect nucleon at larger distance. These are the nature of strong nuclear force. We will make it clear, more clear by observing one graph. Here is a graph of potential energy versus distance between nucleons. X-axis represents distance between nucleons and Y-axis represents potential energy in terms of mega electron volt. Here we are studying about nuclear force, but why the graph of potential energy? Because in physics we understand force as change in potential energy with distance. We understand force as change in potential energy with distance, du by dr. Here we are using graph. From the graph, slope gives the force. We are using negative sign because as potential energy decreases, force is attractive. As potential energy increase, force will be repulsive. Here, suppose slope is positive, force will be repulsive. If slope is negative, then force will be attractive. Now observe the graph. For very short distance, less than 0.5 Fermi, here the distance less than 0.5 Fermi, what is potential energy? Potential energy is maximum. Hence the slope is positive here. In this region, slope is positive. Slope positive means force is repulsive. In region at very short distance, less than 0.5 Fermi, potential energy increases sharply, hence slope is positive. The force is repulsive in this region. For very short distance, nucleons experience repulsive force. Then around 1 Fermi, what happens here? After 0.5 Fermi, as distance increases, potential energy is decreasing. Hence slope is negative here. In this region, repulsive force decreases and there will be small attractive force. Here attractive force increases, somewhere here attractive force will be maximum, and at point R0 here is a deep well, potential minimum. At potential minimum, slope will be equal to 0. At this point, slope will be equal to 0. Hence, at particular distance R0, net force will be 0. Because if distance between nucleons decreases, there will be repulsive force. If nucleons go apart, there will be attractive force. Because of this attractive and repulsive forces, nucleons will be at stable equilibrium. The repulsive force at very short distance will prevent nucleons from overlapping. If nucleons overlap, the nucleus will be collapsed. Hence, repulsive force at very short distance will prevent nucleons from overlapping. Because of repulsive force and attractive force, the nucleons experience stable equilibrium. At deep well, nucleons are at stable equilibrium. Near 1 Fermi, again there will be attractive force. At distance greater than 3 Fermi, for larger distance, potential energy is constant here, hence slope is 0. Again, force is 0. For larger distance, force will be saturated. The effect of force at larger distance will be 0. Here force means strong nuclear force. Around 1 Fermi, potential energy is minimum here. Distance is R0 is about 0.8 Fermi usually. Potential energy is minimum at deep well, hence slope is 0. Force will be 0 at exact minimum. At exact minimum, force will be 0. Hence, nucleons experience stable equilibrium. At distance slightly more or less than 1 Fermi, slope becomes negative, force is attractive. In this region and in this region, slope is negative. Hence, force is attractive. At larger distance, greater than 4 Fermi, potential becomes constant, hence slope is 0. In this region, for greater distance, effect of strong nuclear force is 0. This is the nature of strong nuclear force. I hope it is clear to you. Next comes very interesting topic, that is radioactivity. You heard this term many times, right? What is radioactivity? Radioactivity is nothing but spontaneous disintegration of unstable nuclei. It means unstable nuclei, to become stable, it emits radiation. Hence the name radiation, because it emits, hence the name radioactivity, because it emits radiation. Unstable nuclei, they try to become stable, and to become stable they emit radiation. And this is radioactivity is discovered by Henry Becquerel. And process of radioactivity is independent of temperature, pressure and chemical state. Process of radioactivity is spontaneous. No external force or energy is required, and radioactivity is independent of temperature, pressure and chemical state. Chemical state means the radioactive sample may be in gas state or metal state or oxide state or iodide state, whatever it may be, the process of radioactivity is independent of chemical state. Then types of radioactive decay are alpha decay, beta decay and gamma decay. You will study in detail in next slides. Unit of radioactivity is becquerel. In olden days, unit was curie, but now unit of radioactivity is becquerel. 1 becquerel is equal to 1 disintegration per second. It shows, disintegration per second shows how many radioactive decays are taking place per second. From radioactive sample, how many radioactive decays are taken place per second. This is disintegration per second. Then types of radioactive decay. First one is alpha decay. Heavier nuclei for Z greater than 82, they are unstable. They try to become stable, they come to stable state by emitting alpha particle. Alpha particle means helium nucleus. There are too much number of nucleons inside the heavy nucleus. Hence, unstable heavy nuclei come to stable state by emitting tightly bound alpha particle, tightly bound helium nucleus. When alpha decay takes place, what happens to the nucleus? Here, when alpha decay takes place, mass number decreases by 4. Decreases by 4. And atomic number Z decreases by 2. Because helium nucleus contains mass number, helium nucleus contains mass number 4 and number of protons inside helium nucleus is 2. Here mass number decreases by 4 and number of protons decreases by 2 when alpha decay takes place. It occurs in heavy nuclei because there will be more number of nucleons. Because of that, heavy nuclei are unstable. And mass number decreases by 4 and atomic number decreases by 2. Here is an example. Here, uranium-238 decays into thorium by emitting alpha particle. You can observe mass number is decreased by 4 and Z, number of protons, decreased by 2. Uranium-238 decayed into thorium by emitting alpha particle. The general form is X. Suppose there are Z number of protons and mass number is A, then it decays into daughter nucleus. In daughter nucleus, Z decreases by 2 and A decreases by 4. It emits helium nucleus. Atomic number 2 and mass number 4. This is the general form of alpha decay. What is the nature of alpha decay? What are the characteristics? Alpha particle or helium nucleus is positively charged. Since it is positively charged, it is deflected by magnetic field or electric field. This particle is heavy. Its penetration power of alpha decay is less. It can be stopped by very thin paper or skin. Alpha decay has more ionization power. Since it is charged particle, its ionization power is more. We heard about discovery of neutron and alpha scattering experiment by Rutherford. Discovery of neutron by James Chadwick. For example, in alpha scattering experiment, they took gold foil, very thin gold foil, and alpha particles are projected on very thin gold foil. In these experiments, how do they get alpha particle? How do they get helium nucleus? From this radioactive alpha source. This is how they get helium nucleus as projectile. Okay, this is about alpha decay. Next is beta decay. In beta decay, there are three types. One is positive beta decay, negative beta decay, second one is positive beta decay, and third one is electron capture. When nucleus is very heavy, for heavy nuclei, there will be alpha decay. When beta decay takes place, for lighter nuclei like carbon 11, they undergo beta decay. There will be one excess proton or one excess neutron. That neutron will be converted into proton. Neutron will be converted into proton by emitting electron and antineutrino. Beta minus means electron. Beta minus particle means it is nothing but electron. And antineutrino is another elementary particle which has very less mass, negligible mass, and having zero electric charge. Neutron will be converted into proton and electron and antineutrino. What happens to the nucleus when beta decay takes place? Here mass number remains same because mass of the nucleus remains same, and number of protons, neutron is converted into proton, hence Z increases by 1. Increases by 1. Here is one example. Carbon 6, carbon 14, atomic number of carbon is 6 here. Carbon 14 is decayed into nitrogen by emitting electron and antineutrino. Here you can observe mass number remained as it is, but atomic number increased by 1. That means number of proton increased by 1. Carbon decays into nitrogen by emitting electron or negative beta particle and antineutrino. This is negative beta decay or minus beta decay. And one more is there, that is positive beta decay. Positive beta, we also call it as positron. Suppose nucleus contains excess proton. Proton will be converted into neutron. By converting, proton will be converted into neutron, hence nucleus becomes stable. In heavy nuclei, they undergo alpha decay by emitting alpha particle. For lighter nuclei, there will be excess proton or neutron. Here, excess proton will be converted into neutron by emitting positron. That is beta plus. Positron is nothing but beta plus particle. Mass is same as electron, but charge is opposite to the charge of electron. And positron and neutrino. Here antineutrino, but in positron decay, neutrino will be emitted. And what happens to the nucleus when beta decay takes place? Here A remains as it is, same, because there is no change in mass. And atomic number of protons decreases by 1, because one proton will be converted into neutron, hence Z decreases by 1. Here is example. Atomic number of carbon is 6. Carbon 11 decays into beryllium by emitting positron and neutrino. You can observe mass number remains as it is, but Z decreases by 1. Here why we call it as beta particle? Beta negative is nothing but electron. Electron means electron in the outer orbit. Beta minus is nothing but electron, but it is coming from nucleus. And third one is electron capture. What is electron capture? Nucleus captures inner shell electron. Nucleus captures electron from the inner shell, that is K shell. Hence, proton captures electron and it becomes neutron by emitting neutrino. Proton captures inner shell electron, hence it becomes neutron by emitting neutrino. Here is example. You can observe here mass number in electron capture. What happens to mass number? A remains same. What happens to atomic number Z? Number of protons, observe here, Z decreases by 1 in electron capture, because proton will be converted into neutron, hence Z decreases by 1. This is about beta decay. There are 3 types in beta decay: negative beta decay, positive beta decay, and electron capture. Heavier nuclei undergo alpha decay. Lighter nuclei undergo beta decay. But when gamma decay takes place, when nuclei undergo alpha decay or beta decay, some energy will be left inside the nucleus. Nucleus will be in excited state. It is having some extra energy because of alpha decay or beta decay. This excess energy is released when nucleus comes to stable state. That released energy will be gamma radiation. It is clear that when gamma decay takes place, before that nucleus experienced alpha decay or beta decay. Here gamma decay or gamma radiation is purely energy. Gamma ray is pure energy. It is not having mass or charge. Hence, it is not deflected by electric or magnetic field. And its penetrating power is very high. It can be stopped by very thick lead. Its penetration power is very high. And it has no ionization power because it is chargeless. This is about types of radioactive decay. We have studied alpha decay, beta decay, and gamma decay. This is the summary. When alpha decay takes place, what happens to the nucleus? Mass decreases by 4 and number of protons decreases by 2 in alpha decay. Next, in beta minus decay, neutron will be converted into proton by emitting electron and antineutrino. Number of protons increases by 1. In beta plus decay, number of protons decreases by 1. And in gamma decay, it is only gamma radiation, means it is completely energy. There is no change in mass or number of protons. There is no change in mass number or atomic number because gamma ray is purely energy. there is no change in nucleus. If gamma decay takes place, there is no change in nucleus. Here is one example asked in NEET 2024. In the nuclear emission stated above, the mass number and atomic number of the product Q respectively are. Try to solve it. Here, observe the decay. In first step, there is alpha decay. Nuclei undergo alpha decay. In second step, positron decay. In third step, negative beta decay. In fourth step, again beta minus decay. But it is mentioned as electron. That is nothing but beta minus decay. Let us see the solution. When alpha decay takes place, what happens to Z? Decreases by 2. A decreases by 4. Mass decreases by 4. That is Z82, initially Z82, A290. Initially alpha decay takes place, alpha decay. In alpha decay, A decreases by 4 and Z decreases by 2. Hence, it will become Z minus 2 and A minus 4. In second step, that is positron decay. What happens to the nucleus in positron decay? Z decreases by 1. What is A minus 4 here? 286. Here Z becomes 80. 286. After positron decay, Z decreases by 1. It will become 79 and mass number remains same. Hence it is 286. Third step, beta minus decay. In beta minus decay, what happens to Z? Z increases by 1. Increases by 1, that is Z is equal to 80 and mass remains as it is, 286. And in fourth step, that is beta minus decay. Here in the question it is clearly mentioned nuclear emission. If they have mentioned electron capture, then it would be, then Z will be decreased by 1. Here in the question it is clearly mentioned nuclear emission. That means here electron is emitted. That means it is beta minus decay. Hence Z, what happens to Z? Z increases by 1. It will become 81 and mass number remains as it is, 286. This is the final answer. Hence option D is the correct option. Mass number 286 and atomic number 81. Number of protons 81. In day-to-day life, we use chemical energy source. For example, coal and petroleum. But what is the importance of nuclear energy? Why nuclear energy is so important? And what is the difference between nuclear energy and chemical energy? We will see that how nuclear energy is produced compared to chemical energy. Here, nuclei with less binding energy per nucleon releases energy to become stable. That's why both fission and fusion releases energy. In nuclei, they release energy because of fusion and fission. Unstable nuclei, to become stable, they release energy, or to get more binding energy per nucleon, unstable nuclei release energy. Second point is, in chemical reaction, electron exchange between atoms, whereas in nuclear reaction, nucleus breaks or nucleons combine. In chemical reaction, what happens? You heard about chemical reaction and also nuclear reaction. What is the difference between chemical reaction and nuclear reaction? In chemical reaction, there will be exchange of electrons between the atoms. In nuclear reaction, nuclei split or nuclei combine. Nuclei split means they undergo fission. Nuclei combine means they undergo fusion. This is the main difference in chemical reaction and nuclear reaction. When energy is released in nuclear reaction, then there will be increase in total binding energy. In nuclei, when they release energy, when they get more binding energy per nucleon. If they released energy, that means they are getting more binding energy per nucleon. That means they are become more stable. Chemical energy is due to electron bonds and nuclear energy is due to fission or fusion. How nuclear energy is produced? Because of fission or fusion. And chemical energy is in terms of electron volt, whereas nuclear energy is in terms of mega electron volt. Compared to chemical energy, nuclear energy is very high. Chemical energy is in terms of electron volt and nuclear energy will be in terms of mega electron volt. And 1 kg of chemical fuel, for example coal or petroleum, gives energy in terms of 10 raised to 17 joules. But 1 kg of uranium will give around 10 raised to 14 joule of energy. See the difference? 1 kg of chemical fuel gives about 10 raised to 7 joule of energy, and nuclear fuel like uranium will give energy around 10 raised to 14 joule. This is the difference between chemical energy and nuclear energy. The topic is nuclear fission. What is nuclear fission? Heavy nuclei are unstable. They split into lighter nuclei. Heavy nuclei like uranium-233, uranium-235 and plutonium-239. These heavy nuclei split into lighter nuclei and release neutrons and also large amount of energy. This process is called as nuclear fission. We have studied heavy nuclei undergo alpha decay. But when will nuclear fission takes place? Nuclear fission takes place when nuclei are extremely unstable. And all the heavy nuclei will not undergo nuclear fission. There are only particular nuclei like nuclei of uranium-235, nuclei of uranium-233 and plutonium-239. They undergo nuclear fission. And this nuclear fission is not spontaneous like radioactivity, because external neutrons must be induced in nuclear fission. How? Slow neutron is induced on heavy nuclei like uranium-235. The nuclei of uranium-235 is extremely unstable. When slow neutron is bombarded with uranium-235, what happens? Uranium-235 will split into lighter nuclei of nearly equal mass. Here, uranium-235 splits into barium and krypton by releasing 3 neutrons and also large amount of energy in terms of mega electron volt. Barium and krypton and also 3 neutrons will be released and energy is also released. Here, it is need not to be barium and krypton only. There are other possibilities also, like xenon and strontium. When slow neutron is bombarded with uranium-235, there are some other possibilities of lighter nuclei like xenon and strontium with emission of 2 neutrons, with releasing 2 neutrons, and also energy is released. There is no particular rule that this lighter nuclei should come. That is, there is no particular rule. There are so many possibilities here. It may be barium and krypton, it may be xenon and strontium. And these lighter nuclei, barium and krypton, are become more stable by emitting beta particle. They undergo beta decay, then they will come to final stable state. This is how nuclear reaction takes place when slow neutrons are induced. How large amount of energy is given by nuclear fission? Because of nuclear chain reaction. How energy is released due to chain reaction? We will see that. First point is, the neutrons released in one fission strike other uranium-235. Here, in one reaction, there will be 3 neutrons released. These neutrons are used in further reaction. This is how chain reaction is formed. This self-multiplying series is called chain reaction. If chain reaction is controlled, then we call it as controlled chain reaction. Controlled chain reaction is very useful in power generation. In nuclear reactors, we use controlled chain reaction. If it is not controlled, enormous amount of energy will be released that will lead to explosion. It will become atomic bomb. If it is controlled, it can be used in generation of power. What are the applications of nuclear fission? Electric power generation. Yes, controlled chain reaction. Controlled nuclear fission is used to generate electric power. Then is nuclear weapons. Uncontrolled chain reaction is used in nuclear weapons, that is atomic bomb. Next is radioisotope production. Nuclear fission is useful in medicine to produce radioisotopes. These are the applications of nuclear fission. Next is nuclear fusion. Just think, you have a setup or machine that can generate energy equivalent to energy given by 10,000 tons of coal burnt by using 1 gram of hydrogen. Is it possible? Yes. In nuclear fusion reaction will give that amount of energy, that much of enormous amount of energy. What is nuclear fusion? Here, lighter nuclei combine to form heavier nuclei and release energy. When they become heavier nuclei, their binding energy per nucleon increases. Hence, they release energy when they become heavier nuclei. This is nuclear fusion, the process of nuclear fusion. And nuclear fusion releases enormous amount of energy due to higher binding energy per nucleon. It occurs naturally in stars including the sun. The best example of nuclear fusion is the sun and stars. They exist because of nuclear fusion. There are important conditions for nuclear fusion to take place. What are those conditions? High temperature. For nuclear fusion to take place, there must be temperature, very high temperature, about 10 raised to 8 Kelvin. Very high temperature. What is the boiling point of water? 373 Kelvin. We can't touch even boiling water. Then think of the temperature of 10 raised to 8 Kelvin. At this temperature, everything on the earth melts. At this temperature, even atom melts. Atom diffuses into free electron and ions. Electrons will come out of the atoms. They will become free. And left is ion. In nuclear fusion takes place for lighter nuclei. We will take the example of hydrogen. When we give temperature of 10 raised to 8 Kelvin for hydrogen, what happens? Hydrogen contains one outer electron and there will be single proton inside the nucleus of hydrogen. What happens? Electron will become free and there will be proton, that is positively charged ion. There will be formation of ion. This state is called as plasma. Plasma is nothing but when high temperature is given, atom diffuses into free electron and ion. This state is called as plasma. In this temperature, in very high temperature, what happens? They will start to move faster. They will have more kinetic energy. Because of that kinetic energy, they overcome Coulomb force. There will be so many number of hydrogen atoms. Because of high temperature, the atom diffuses into free electron and ions. What happens? Because of very high temperature, proton will not have repulsive force because of very high kinetic energy, and proton electron will not have attractive force because of very high temperature. They will have more kinetic energy. Hence, at this temperature they overcome Coulomb repulsion. And also second condition is, for nuclear fusion to take place, there must be high pressure and high density, because it increases probability of collisions. When there are more number of hydrogen atoms and if pressure is also very high, what happens? There is probability of more number of collisions. If number of collisions are more, there is more possibility of combining. That means more possibility of nuclear fusion. Third condition is sufficient confinement time. What it means? We should provide this high temperature for longer time. If we provide this high temperature for longer time, the probability of collisions will be more because time duration is more. Hence, energy released will be more and resulting plasma. That means when we give very high temperature, there will be formation of plasma. Atom will diffuses into free electrons and ions. This is the state of plasma. Plasma is a fourth state of matter at very extremely high temperature. These are the conditions for nuclear fusion to take place. Energy is generated in stars. We will see that. Scientists decided to set controlled thermonuclear fusion because even though nuclear fusion releases enormous amount of energy, we don't have single fusion reactor on Earth because it needs some conditions. In previous slide, we have studied about conditions for nuclear fusion. Because of those conditions, it is difficult to set up fusion reactor. But scientists are trying to set up fusion reactor called controlled thermonuclear fusion. Thermonuclear fusion means by providing very high temperature about 10 raised to 8 Kelvin, the fusion process is achieved because very high temperature overcomes Coulomb repulsive force. This process is called as thermonuclear fusion, and scientists decided to set up nuclear fusion. That project is called as controlled thermonuclear fusion, and aim of this project is to replicate this fusion process on Earth to generate energy, because energy released due to nuclear fusion is much more than energy released due to nuclear fission. We have studied nuclear fission. Nuclear fission releases large amount of energy in terms of mega electron volt, but energy released due to nuclear fusion is much higher than energy due to nuclear fission. Of course, energy released due to nuclear fusion is much more than energy by chemical sources. This is why scientists are decided to settle this thermonuclear fusion reactor. What happens in nuclear fusion? Lighter nuclei combine to form heavier nuclei and release energy. Here there are some nuclear reactions, fusion reactions given in your NCERT textbook. By observing these reactions, you can clearly understand what happens inside the star, how energy is generated in stars. At extremely high temperature, what happens? Hydrogen is a lighter. A hydrogen nuclei is lighter nuclei. It contains single proton and one outer electron. At extremely high temperature, electron will become free, and there will be positive ion also. That state is called as plasma state. When high pressure and high density is given, at high pressure and high density, what happens? Because of strong nuclear force, proton and proton will combine. That's why we give very high temperature. They should overcome Coulomb repulsive force. Proton will combine with another proton and it becomes deuteron, nucleus of deuterium, and releases energy. By releasing positron and neutrino, it also releases energy in terms of mega electron volt. Here positron is released, and in plasma there will be so many number of free electrons. What happens? This positron will combine with free electron and again energy will be released. Now observe first reaction, fusion reaction. Here deuteron, there will be formation of deuteron. Here this deuteron will combine with another proton and it becomes helium isotope by releasing some large amount of energy in terms of mega electron volt. When this reaction takes place many times, there will be so many number of helium isotopes, and helium isotope, one helium isotope will combine with another helium isotope and becomes helium nucleus by releasing protons and two protons and enormous amount of energy in terms of mega electron volt. This is how fusion chain forms, and this is how energy is generated in stars. What is the goal of controlled thermonuclear fusion? Because of controlled thermonuclear fusion, we can generate steady and safe energy, not a bomb. Controlled thermonuclear fusion, hence it is not a bomb, to generate steady and safe energy. And next is use abundant fuel using deuterium. Deuterium is abundant in nature, available in water. Using seawater, we can generate enormous amount of energy due to controlled thermonuclear fusion, and produce clean energy with minimal radioactive waste, and also provide almost unlimited power for humanity. To provide unlimited power, this controlled thermonuclear fusion, the aim of this controlled thermonuclear fusion is to provide almost unlimited power for humanity. But what are the challenges to set up controlled thermonuclear fusion? It requires very high temperature, about 10 raised to 8 Kelvin, and atoms becomes plasma at very high temperature, extremely high temperature. Everything on earth melts. If there is formation of plasma, which can hold that plasma? No physical wall can hold plasma. That is the main challenge. No material container can hold plasma. Okay, that is the meaning. No physical wall can hold this plasma. Then how to hold plasma? Because of strong magnetic field, we use magnetic confinement. Because of only strong magnetic fields can deflect those ions and charged particles. Without touching plasma, only magnetic confinement can hold this. It acts as magnetic bottle. And main challenge is plasma confinement, that to hold plasma, that is the main challenge. This is about nuclear fusion. This completes the chapter nuclei.